Hi, this video is about the connection between electricity and magnetism. Let's start with a compass. A compass is really just a piece of metal that is allowed to move around freely. This piece of metal here is suspended and it's rotating, and it always seems to point the same direction no matter what I try to do. It's pointing along Earth's north and south directions. This is because the Earth is a big magnet, and compass needles always follow a magnet. I can prove that by just showing you what happens if I take a magnet and bring it next to this compass needle. It always wants to follow wherever the magnet goes. So that means if I let it go, it just lines up with the other magnet, that is the Earth. The Earth is a big giant magnet. So compass needles allow us to tell if there is a magnet present. That's important because what I want to show you now is just a simple electric circuit here. I've got some batteries, and I'm going to connect these batteries to a light bulb and a switch. Okay, and so by kind of lining all these up here and turning on the switch, I get some current going through my circuit. You can see that here with the light bulb turning on. Also, you can see it here on my ammeter, which measures amps. Now, what was discovered, it was discovered by a man named Hans Christian Ørsted, and he discovered one day as he was playing around with circuits that as he left a compass needle near one of his circuits, he noticed that the compass needle did something when he turned on the electric circuit. So watch this compass needle as I turn on the circuit. You'll have to watch close here. All right, did you notice that? Right now it's lined up with the Earth, but when I turn on my circuit, the compass needle realigns a little bit. There must be some kind of magnetic field that wasn't there before. It's only there when I turn the circuit on. And that's kind of unusual because there's clearly no magnets present right now, but the presence of electricity, and specifically moving electricity, current, that produces a magnetic field. And so what Hans Christian Ørsted discovered was that, keep my circuit going here, a moving electric charge or electric field induces a magnetic field. This word induces simply means it influences or causes to come about. It just makes it happen. So a moving electric field can induce a magnetic field. We see that here with my compass needle. Now, after doing some more experiments with this, they were able to kind of determine that if you take a wire, and let's say I'll just take one of these wires here. If you take your wire and measure how the magnetic field around it looks, then the magnetic field actually kind of wraps around the wire, kind of like my fingers wrapping around it here. If the current's going through this way, the magnetic field points around it. And I'll try to show that to you here. If I just draw like the wire, if this is the wire coming out towards you, then the compass needle always tends to point in a circle as you move it around the wire. So this is the shape of the magnetic field in some sense. It goes around the wire. Now, that's pretty interesting, but it's not very useful. But later, people realized that as you take a wire and you wrap it up in a circle, you can sort of concentrate that magnetic field. In fact, if you do multiple loops, you're kind of looping a magnetic field around itself. If you have current going through this wire, you can produce a pretty strong magnetic field. And so that's what some people tried to do. And I've got an example of a really big coil right here. This is just a piece of wire that's been wrapped 100 times at least around in a circle. And by doing that, you can connect it to a current. And I'm not sure if this is going to be enough voltage because this is a lot of wire. The more wire you have, the higher resistance you have here to electricity passing through. Let's see if I can get a current going here. We'll see if it's enough. So I've got the batteries connected to my coil, and then to the ammeter here, and then I'm going to connect that to the battery. We do get some current, so that's good. A little bit of current going through this coil right now. Now, as a result, this coil is producing a magnetic field. And I'm not sure if this is strong enough to actually measure. Well, let's try it out. You can actually cause it to be a little bit strengthened by placing a piece of metal in the middle here. So I'm going to place a piece of metal inside this coil. And let's see if this piece of metal has any magnetic properties now. It does appear to be influencing the needle. If I move the needle up here, it goes back to the earth. But if I bring it down here, yes, I'm very clearly getting a magnetic field. If I disconnect the battery, I wonder if the magnetic field goes away. It does slightly. It's already kind of magnetized this piece of metal though. Yeah, you can see as I reconnect my battery here and get the current going again, it does cause this compass needle to kind of deflect a little bit to move. So we have essentially created a magnet using pure electricity. So again, a moving electric field induces a magnetic field. Well, that's really interesting too. What if we disconnected our voltage source here, so we no longer have a source of potential energy from the electricity. Instead, we simply have just a coil of wire and an ammeter just to measure current. Now, if I connect this right here, there should be absolutely no current because there's no voltage right now. And sure enough, I have no voltage. Now, this little piece of metal here is not magnetized. I can show you that with a paper clip that I put somewhere. Here's one. So I got a paper clip here, not a magnet. Okay. This is a magnet. It picks up the paper clip. So this is not a magnet right now, but I can make it a magnet by attaching some stronger magnets to it. So I've got some neodymium magnets. These are pretty strong. Got to be careful with them because they will shatter. I'm going to just attach it to the end here, making this a pretty strong magnet. Okay. Now, I wanted to make this into a magnet, this specifically, because it fits nicely into my coil here. And I wanted to show you a discovery that was made when you take a coil and you put a magnetic field inside the coil. So right now there's no current, there's nothing. I do have a magnet here. But as I move this magnet close to this coil, if you watch my ammeter here, okay, right now I have no current, but as I move the magnet in and out of the coil, you'll notice that the current peaks a little bit. I'm actually causing it to move. And if I rotate the magnet or if I push it through faster, I can get a little bit of current coming out. And this is a pretty big discovery. It actually is just the reverse of the first discovery. We've discovered now that a moving magnetic field, or a moving magnet, can generate or induce an electric field or a current. Now, this discovery was incredibly useful because if you can suddenly generate electric current without the need for batteries, without the need for, some kind of voltage source that drains out, if we simply can just take a magnet and move it inside of a coil of wires to generate electricity, then we suddenly have a really plentiful source of electricity. All you need is something that can move a magnet. And so people like Michael Faraday discovered that if you arrange magnets and coils and wires in certain ways, you can generate electricity. You can create what's called a generator. And this is where we get most of our electricity today, is from a magnet that's moving inside of a coil of wire or a bunch of coils of wire. So this whole idea is known together as electromagnetic induction. And it says that a moving electric field or a current induces a magnetic field, and likewise, a moving magnetic field induces an electric current. So that's all I've got for you in this video. Remember, shortcuts make long delays.